Good morning, everybody. It's a great pleasure for me to be here for the first time at Vienna. And so far, I loved everything, the city, the people, the food, the schnitzel, the ribs. And you have particularly great white wine. The red wine, maybe we can improve that, but white wine is awesome. Okay. And I'm very glad to be here to be talking to you today about migrating to microservice databases. Basically, which means I've been talking about microservice for like 2 or 3 years now. And the number one question that I always receive when talking about microservice, okay, usually people recommend you to break up your monolith into microservices, but you have this thing that each microservice must have its own database. But I have a huge monolithic database. How do I break it into smaller microservice databases? And later, how do I integrate this data? So I've proposed myself to try to answer this question. That's why I've been researching this subject on the last year and a half. I talk about with many different people and teams worldwide and try to collect a set of solutions that people are applying to solve these problems. And I collected these, and I hope to be able to show you some of this today. My name is Edson Yanaga. I'm a director of developer experience at Red Hat. My Twitter handle is @Yanaga. And I hope that you'll be able to pronounce Yanaga because I'm a Brazilian Japanese. So Yanaga is very easy to speak in Portuguese and in Japanese, of course. But I realized that usually Americans, particularly, they can't spell they can say my name correctly. So they just call me, at least in the US, they call me Mr. Why because they don't know how to say Yanaga. I hope it's not a problem here in Austria. And I'm also a Java champion and a Microsoft MVP, which is kind of weird to have both titles these days. But it just shows you how the world has changed in the past few years. And I've always been advocating for open source software. It's a great pleasure for me to be employed by Red Hat, to be a Java champion, and to also be an MVP, because in the end, it just means that open source in the end has won. So there's no battle about it anymore. And about the subject that I'm discussing today, I've just launched the book from O'Reilly, Migrating to Microservice Databases. I even have a few printed copies that you'll be able to pick some here. I just ask you to, if you wish to, just follow me on Twitter @Yanaga. But if you wish to get the ebook for free, Red Hat bought the royalties for the book, and it's available for you as a free download at this site. But you don't have to type the whole URL. You can just access developers.redhat.com, and you'll be able to download the free book. For you, that's a technical report book. I think it's a quick read, and I hope you'll be able to enjoy the information that I'll be able to present to you today and later on the book, which we have much more time and space for detailed information. And I always like to start my talks with this sentence, which is not from me, but from Forbes. Now, every company is a software company. I like to say that you don't work for the government, you work for a software company. You don't work for a bank, you work for a software company. You don't work for an industry, you work for a software company, because in the world that we live today, we're all being changed by the digital transformation, the digital revolution that is happening with our daily lives. And some great examples of the companies that are changing our lives these days is that the largest car transportation company in the world owns no cars, which is Uber. The largest lodging company in the world owns no real estate, which is Airbnb. The largest online retailer in the world owns no stock, which is Alibaba. And the largest content network in the world produces no content, which is Facebook. All of these companies, they have something in common. They only exist and they only live because of software. So software is changing the world, it's changing the people's lives for the better, and also software can change people's lives for the worse. I always like to introduce myself also as software craftsman. And we have many different definitions of what is a software craftsman, but the one that I like the most is that a software craftsman is somebody that cares about what he does, or he or she does, and he or she cares about the impact that his job has in the lives of other people. Because we know what is to be miserable when using software that is not up to our expectations. And Some years ago, I had many different moments when I realized that I was making people's lives miserable with the software that I was delivering, because even though the software fulfilled all of the requirements, even though I think I did a good job, I was crafting good code, I was testing, and I was doing everything that I thought it was good enough. When I saw my software running in production, I realized how miserable the users' lives were. So I made a choice. I decided that we could change people's lives for the better. And I know that if you're all here trying to improve yourselves as software developers, you're all trying to improve people's lives for the better. And I thank you very much for that. And the discussion I'm going to have you today about DevOps and microservices. I'll just choose one topic to be talking about that, and that's the feedback loop, because we depend on the feedback loop to improve everything that we do in our daily lives. And so with software is not different. The shorter, the better, and the more amount of feedback that we have when developing software, the better the result that we have into production. But if I have to choose just one technical term to discuss with you about the feedback loop, this technical term is called the batch size. And for many of you that are used to Kanban, Q theory, or DevOps, the batch size is the amount of things that you deliver into production into each one of your releases. So the larger the batch size, the lower the quality of what you deliver into production. So if you think about the batch size, if you could reduce dramatically or increasingly the size of our batch size until we have an ideal size of like 1 commit per deployment. Then if we can have a faster feedback because we can have a smaller cycle time, we can have a smaller lead time, so that you can quickly access if you're doing the right thing into production. So when we reduce our batch size, we can have 2 improvements. We can know if you're doing the right thing, and if you can know if they were doing the right thing right. So imagine if you can code a bit and just deliver that into production. If anything goes wrong into production, we quickly know where's the problem, because we just changed it like that 50 lines. And if anything went wrong into production, we know exactly where the problem is. And for business people too, imagine if you can quickly assess what is the impact of doing some modification to the software into production. Are we going to sell more? Are we going to allow our users to spend less time on our software so they can produce more things in the smaller amount of time? If you could quickly access that by reducing our batch size, also the quality of people's lives would be better too. So we're always trying to reduce our batch size to the minimum possible amount. And I'm not saying that you must be Amazon, which does a deploy like every 13 seconds, I think, or you don't need to be like a Netflix, which can deliver one deploy like in like 10 minutes or 15 minutes. But many of us, we can reduce the amount of batch size if deploying software every 6 months. Maybe you can do like every 3 months. I just talked to a customer on Monday, and he was saying that they only release software once a year. And maybe they could improve like at least twice a year, and so on. Which, okay, twice a year every 6 months doesn't look good, but if they're releasing like once a year, then it's 2 times better. And maybe if you work for a bank, you won't be able to deploy like every day or 2 times per day, but maybe you can release software like once a week. I know that in the bank industry, you have a lot of compliances to be aware of. So 1 week maybe is your ideal batch size. So you can work that. You can always improve. But even if you try to improve a lot, even if we could be able to deploy like in every commit, in every minute or every hour, there's this thing called maintenance window, which is not controlled by our developers, but by the ops guys. Because even we could deploy more times per day, we usually are only able to deploy our software in the maintenance window, which is the time frame where the ops guys say, okay, you can just take your application server down and deploy the new version of your software, because we're not allowed to disrupt users into production. So the maintenance window usually is scheduled for once a month or once every weekend or like once every night. And usually that's the times where you don't want to be deploying software, because you want to have a life. You want to to have your weekends back, your nights back. You don't want to be spending like 3 or 4 hours every evening trying to deploy software. But for us to be able to reduce our batch size and to deploy software more often than the maintenance window that we have into production, we need something called zero downtime deployments. And for zero downtime deployments, we have one clear requirement, which is to have we need at least what we call blue-green deployments, and I'm going to explain very quickly to you what does it mean. For blue-green deployments, usually traditional architectures have your clients issuing requests directly to your deployments. In a blue-green deployment, we need to add another component to our architecture, which is a proxy. So it can be a reverse proxy, a load balancer. In this case, we have many different software that is capable of doing this. We're just calling it proxy because it's just an intermediate component that is intercepting the request for us. So usually the proxy is just forwarding the request to our backend deployments. For our blue-green deployments, we're going to have 2 different deployments, which is the blue and the green one. And they all will have equal capacity because each one of them must be able to handle 100% of our requests in productions at a given time. So you're not doing just plain load balancing, even though you could. Think about blue-green deployment, you're going to have at least a failover environments for you. So that's a better approach to think about that, because now you need like to double your server environment to have all of your requests. And the blue-green deployment works basically if we have a new release of software. Think about the blue is the current one, and the green will be the new release of software that we're deploying. We just take the green deployment server down, you copy the new artifacts, you start up your server again, maybe you even reboot it, you wait for the server to warm up, because if you work with Java application servers, you know that sometimes your application needs a time to warm up and you need some few requests, test requests to warm the server up. When everything is okay, the server is warm and back again, then you can switch the router and get the request to be serviced by the green deployments, and you can do the same process with the blue deployments. You can shut it down, copy the artifacts, you can start it up, wait for it to warm up, and when everything is okay again, then you can just put the blue deployment into production again. And then you realize that if anything went wrong with my green deployments, with my new version, for me to have the previous version working on production is just a matter of switching back the router without updating the blue deployments. And so it goes on. So this approach allows you to have zero downtime, because no request will have an error while you're updating your deployments. And also, you have a easy fallback. You can easily roll back your previous version by not updating the other deployments before that goes into production. So it's not only allows you to have zero downtime, but it's also a much safer approach to releasing software into production. But then you think one of the problems that we have here is that we have 2 different versions of our software running into production, and you guess maybe something has changed between the versions, and maybe these versions are incompatible. So for you to have a true zero downtime deployment, you need to have back and forward compatible versions when you deploy into production. But even if you were able to create like code compatible versions of your software, your new version and your older version, I like to say that usually with code is easy and state is hard, because with code is just something that you update, owns no state. When you have to change your state from one version to the other, that's the hardest part. And I'm not saying really that code is easy to do, because we know that especially good code is very hard to craft. But no matter how hard or how easy it is to craft your code, state is always harder. And when I'm talking about state, when you deploy software into production, we have 2 different kinds of state. We have ephemeral state, which is usually stored in the HTTP session of your server environment. We also have persistent states, which is usually stored in a relational database for enterprise software. And so the question that I like to answer to you today is, what about my relational database? How do I do zero downtime upgrades with relational database. And first of all, we need some tools for us to be able to do that. We are not allowed anymore to do manual updates to our relational database. The technical term for the amount of things that you change on the schema of your database between versions is called migrations. So usually you have this huge SQL script that you send to your DBA, and the DBA applies that during the night when you can safely change the schema of your database. Usually you mail that to him, or you create a ticket for him, and sometimes he forgets to apply the database scripts, and which makes your application breaks into production. Then we need to automate that. For that we have some very cool tools. The most popular ones in the Java world are Flyway and Liquibase. They're both feature complete by now. I mean that they're both comparable in terms of functionality. My particularly favorite is Flyway, but just because I like it more, not because it's better or worse. But I decided to use Flyway some years ago when I realized that Flyway could be used also if you have an Android application and you use the embedded SQLite database that you have in your Android application. You can use the SQL Droid, which is a JDBC driver for Android. You can use Flyway on your Android applications too. So we were able to use the exactly same tool both on our server environment on our mobile environment. So that's why I chose Flyway. And by the way, I patched the SQL Droid JDBC driver, and I deployed that to the Maven Central. So if you happen to be using the SQL Droid driver for Android, I've made it work with the most recent versions of Flyway and Android. So, and if we've automated, we're not allowed to just be applying our SQL scripts anymore for migrations. We need a tool for that. And what I'll show you now is how we were able to achieve zero downtime migrations when using automated tools like Flyway or Liquibase. So the first answer, which is the obvious one, their migrations need to have schemas that are back and forward compatible between versions. You also have to break your schemas with babe steps, which means the smallest possible batch size. You're not allowed anymore to issue like multiple alter tables or multiple updates in each one of your migrations. Your migrations most likely will be like just one SQL statement per migration. You also have to avoid locking, because if you issue an update statement to your database or an alter tables, which is the case, won't be possible. But if you have an update statement that you have a table with like 1 billion rows, and your update statement takes a long time to work on that table, you're going to have a lock time, and this lock time means downtime into production. You're not allowed to have this lock time anymore. So to avoid these long locks, you have to shard your updates. And shard is a very neat term for database, which means you just split your data set in smaller amounts, so you can, it's for that each update statement that you issue to the database is going to take fewer amounts of time. How much? It really depends on your application. If you issue an update statement, it takes like 1 second. Maybe 1 second is a reasonable lock time for you. Maybe it's not. So it really depends on your environment, really depends on your use case and everything else. But I always recommend for you, doesn't matter the amount of your data size, your data set, doesn't matter the amount of lock time that you're allowed to do. You have to rehearse your migrations up to exhaustion before applying that into your production database environment, okay? So you'll be able to check how much time it's going to take for me to issue that. Once I did that, I had a bug into production. We released the software on the same date, and it was like 3 p.m. It was a health insurance application, and we had a bug. We just said it's just a minor bug. We're gonna have like a 2 minutes downtime to update that into production, but so we'll be able to do that. But unfortunately, on that day, one of the programmers, they just committed the schema update of Hibernate to true, and they just changed a property of an entity, and we deployed that into production. And when we saw the database was issuing an alter table statement to add a new column, to modify a column into production, and the alter table statement took 1.5 hours to be completed. Yeah, it was an old version of MySQL because it was like 10 years ago. But well, we had a very painful day. when we decide to update that, because like 1 hour and a half in the middle of the day for a healthcare application, it wasn't the most pleasant day of my life. So you have to avoid this kind of locks when you try to do that. And one way for you to shard your updates, I'm going to show you how you refactor that. So you're never going to issue anymore this alter table, rename column, something to other thing. Then instead of just issuing one single SQL statement to the production, you're going to have to split these statements into multiple statements. So instead of just renaming a column, you're first going to add a column, then you're going to copy the data multiple times with shards until you with smaller shards to avoid lock time. And when all of your data is copied, then you can finally, much later, when you know that you're not using that column anymore, maybe then you're able to just delete the column because you know that your application is not used anymore. And I'll have to say to you, delete alter table, delete column is a destructive statement, and destructive statements are not backward compatible because you simply lose the data. That's why you're not allowed to do that into production when you want zero downtime, because you need the versions to be back and forward compatible, because if anything goes wrong, you always can roll back to the previous version. So I've collected some scenarios with different teams worldwide. The most common ones are add a column, rename a column, change the type or format of a column, and delete a column. And you see, I didn't cover tables, because if you think of tables as a set of columns, then any kind of migration that you can apply to columns, you just have to do it multiple times if you want to change the table. So it's not that rocket science. So what do you need to do if you want to create zero downtime migrations to add a column? First, each one of these numbers, 1, 2, 3, and 4, are different steps that you need to apply to your database, each one in a different version of your software. So first version, if you want to add a column, you're gonna add a column, and you're not gonna use the column yet. The second version of your application, your code is gonna compute the read value and then write to the new column. Because you can have a default value, or maybe the value that you're storing on the column can be calculated from other columns. Then you release a new version. Then the first version, you're going to update the data using shards if you're allowed to do so. Because if you have a default value, you just populate that using shards. If you can compute that, you compute and store into the database. And the fourth step, code reads and writes from the new column. So add a column is the simplest one. If you do this in 4 steps, you have back and forward compatible versions between each one of them. And I also have to say, it's also safer because between each one of these steps, you're going to take and open your database CLI, open it, and going to issue like select statements to check if the data that you're applying to production, if it's right, if the data that you migrated is working correctly, if your application is writing the right values to your database. So you need to check your database state between each one of these steps, because you want to play on the safe side. You don't want to disrupt your data into production, and this way you are always safe. You're never going to issue destructive statements into production. Add a column is the simplest possible use case. Then we have a more complex one, which in case is the most complex one, which is to rename a column. To rename a column, you need these 6 steps, at least 6 steps. So first, you're going to add a column. Second version, your code reads from the old column and writes to both columns. Third step, you're going to copy the data using small shards until all your data is complete. Fourth step, your code reads from the new column and still writes to both. You might be asking, why are we writing to both columns on the same time? Because we need our versions to be back and forward compatible. We don't want our new version needs to write to the old column, because if you roll back a version, the data is still there, and so on. So the 5th step, the code reads and writes from the new column because everything went right on the previous step. And much later, if you decide, the migration is done, everything is worked correctly, then you just don't delete the column now. You just mark the column, you create a ticket, or delete this column later. So maybe after some weeks or months, then you know that nobody is using that column anymore. Then you'll be able to, the database, when he's using the cleanup of the database, then the DBA maybe he or she might issue the delete column because you're pretty sure that nobody will be doing that anymore. And again, if you do this on the safe steps, you're never gonna have to rely on the database backup to recover your data, because again, we're never creating a destructive statement into production. Our database is always safe. And next use case, change type and format of a column. And if you look closely, you can see a pattern here. To rename and to change type or format of a column. These are all exactly the same steps if you want to refactor your database, to restructure your database with zero-downtime migrations. And that's a good thing because we're always rehearsing the exactly same steps. Then you just need to apply. There's at least 6 steps for you to have zero-downtime migrations into production. Fourth one, delete a column. Simply don't delete a column into production. You're right, it's a destructive statement. If you delete a column, the only way for you to recover the data that was there is to get the backup and put it back into production. And really, you don't want to do that because it can take like many hours for you to recover a backup. And the state has changed already before you notice that the data was wrong or that you needed the data that was there before. So you never delete a column into production because that's a destructive statement. You just simply stop using the read value, but you keep writing to the column because, you know, backward compatibility. And much later, if you realize, oh, really nobody's using that thing anymore, we just released in multiple versions already, and that column data is not needed anymore, then you just mark the column to be deleted by the DBA like much weeks or months later. So that's how it works for zero-downtime migrations. And you might be asking also, what about my referential integrity constraints? And the answer is you have just to drop and recreate when everything is done. If you think about it, you don't need referential integrity constraints to your database for application to work. Referential integrity constraints are just like safety nets for your database for your application to not behave incorrectly. But so I know that I'm advising you to just drop when you're changing things, which is usually the moment that you want the safety net, but sometimes you need to break some walls to make room for improvement, and that's exactly the same if you're creating zero-downtime migrations, then you might need to drop these constraints. Not null constraints, by the way. Also, if you want to create a not null column on the beginning, it will have to be a nullable column, and then when all of your migrations are done and you just completely restructure a database, then you'll be able to add a not null constraint. But in the beginning, all the columns are nullable because they will have null values. Okay, that's a step for zero-downtime migrations, which is absolutely important for microservices database. If you think about, if you were allowed to have downtime when you have a monolithic database, now that you have multiple microservices with each one with its own database, then the downtime would be multiplied by at least the amount of microservices that you have. So you're not allowed to have a microservice to have downtime. In fact, you're not allowed to have your system to have downtime just because one small piece of it, just this microservice, is having downtime because of your database. That's why zero-downtime migrations are so important, and that's why I chose to discuss this topic here today. But talking about specifically microservices, we have some microservice characteristics that I'm pretty sure that any microservice talk will approach. But the one that I chose to be discussing with you today is just this one, decentralized data management. We need to, if we have a huge monolith and we want to split our monolith into smaller microservices, then we need to extract my microservice database because we have the principle that each microservice must have its own database. So we have many microservices, each one its own database, but in fact, that's the recommended approach. Usually we don't start an architecture by creating microservices. We usually just start creating a monolith, and when it's big enough, we break it apart, because breaking it wrong is possibly one of the worst things that you can do to your application. Because instead of leading to the loose coupling that you want in your application, you have tight coupling, and then you have some microservice anti-patterns, like if I change here, I need to change this microservice too. If I change here, I need to change this other one too. And you know, it's a basic principle of software architecture. Things that change together stick together. That's the same principle for modules, for object-oriented code, and now for microservice architecture too. And in the beginning of our application, we don't have enough knowledge of our domain model to know which kinds of things change together and which kinds of things change apart. But when you do have the knowledge, which means many months or even years later, when you know that, oh, this part of the table is stable, usually the modifications are confined internally to this part of the system, then this is the ideal candidate for a microservice. When you want to split that, then you have, for a given amount of time, maybe you have your monolith and your microservice accessing the same tables on the same database. But then, when you realize that you've just splitted the domain model correctly, then now it's time to split the database. Then you might have some possibilities for splitting and later integrating the data back to your system. So I'm not going to discuss how do you choose which parts to split, which is the topic of discussion of another session. But today, well, you just selected which tables you can split in your database. But when you've decided, oh, these tables will live in this microservice and the rest of the tables will keep living on my monolith or maybe in another microservice and everything else, but your system is not an island. Usually, if you decide, like, I have a system, I have a customer database with all of its dependencies, and I decide to create a customer microservice. Okay, so the customer microservice will be the canonical source of information for my customer, but the rest of the system, everything else needs the customer information. So the obvious thing that people do, oh, I'm just going to create a customer microservice. I'm going to expose this information through a REST endpoint, and all of the rest of my monolith, I'm going to create a DAO. And I'm going to issue HTTP requests to this microservice, and I'm going to get the microservice, the customer information. Then when you deploy that in production, you just realize that you fail miserably because it doesn't scale, because it just gets so sluggish, and because you realize that the HTTP has its own costs, and you realize also that all of that distributed system fallacies, that it's not reliable, it's slow, you have a huge latency. And even though, the networks are fast these days, we have like 10 gigabytes per second internal networks that we can use into production. Okay, throughput is not an issue for most applications, but latency is. So no matter how performant is your network, latency is still an issue for network communication. So you realize that it doesn't work quite well when you just decide to split that. Then you need some techniques to be able to integrate this data from your microservice into other parts of your system. And let's discuss this. So splitting certainly is not easy, but integrating is neither. So I've just splitted how to integrate my data that I've just split into the rest of my system. So for the purpose of clarity, I need to first discuss some consistency models. I know it's a very hard topic on distributed systems, so I'm going to oversimplify the concepts for you now. And I'm going to choose just 2 different consistency models because that's the one we're going to apply here today. We can have strong consistency and eventual consistency. Strong consistency means that if we have 2 nodes in the distributed systems, if I write to one node, if I write variable a is 5 now, then in a strong consistency model, all of the nodes in the system, they must agree on the new value before the value is exposed to the clients. So until everybody agrees, okay, now the value of a is 5, nobody's going to be able to read this new value in the system, okay? That's a strong consistency model, and usually that's the way that we think about when talking about transactions. But then you realize that most databases that we use, they don't have a strong consistency model, because if you can, you don't use serializable transactions, you usually use repeatable read transactions, and that's not strong consistency. Then you can fall back to another model, which is eventual consistency, which means that people can read the value while the value is being updated. And I'm just going to explain a very particular case of eventual consistency, which is strong eventual consistency, because that's the one we apply in microservice architecture. Imagine if I have a customer microservice and the rest of the system. The customer microservice owns the customer model, so the only microservice that can update the customer database is this one. So if only one node in the system is allowed to change the information, then we can we have this strong eventual consistency model, which means that you update the information here, And the other nodes, they still can have outdated versions of the information that is here, okay? So the other nodes, they never have a wrong information. They just might have an outdated information because it takes some time for the information that was written here to be propagated to the other nodes. And if you think about it again, our model, our domain model, the real life model is always eventual consistent. Because if we create a query into our database to know how much money we have in our bank account, just during that database transaction, there is a strong consistency. But when the information gets through the network and you see that on your web browser, that information might be outdated already. Then we're always dealing with eventual consistency. We just need to apply this kind of knowledge to our domain model when to our architecture too. So our real world is eventual consistent. When you get the business person ask you for a report, I want a report of the consolidated sales of this month. When he sees the printed report, it's already outdated. So it's always eventual consistency. So we need to free our minds. We don't need to think strictly about strong consistency because the distributed world and the real world is always eventual consistent. And in our particular case for microservices, it's always strong eventual consistency. Okay? You will have some special use case where it's not true, but for sake of simplicity, let's assume that it's true. We also need to discuss these two popular architectures, CRUD and CQRS. And I know that many of you have heard or read many things about CQRS these late times. And I know that many people have different concepts about what is CQRS. I'm going to try to explain in a very simplified way for you what is CQRS regarding data models. So when you have a CRUD architecture, which is the most simple possible architecture, in fact, it's the most appropriate architecture for like 90% of the use cases. You have all of the create, read, update, and delete operations. They are issued to the same database, to the same set of tables, using the same model. So if you're programming in Java, it means that you're going to have the same classes, customer. You're going to use the customer class to save, to read, to update, and to delete. Okay, you always use the same domain data model for all these four informations, and it's also the simplest one, and it's the same tables. When you have CQRS, which means command query responsibility segregation, it means that you can have a different domain model, a different set of classes for the read operations and a different set of class for the write operations. You might have the same database, the same tables and columns for the read-write model, the same database, but you have like, maybe you're gonna update your database using the customer class, but then the customer has too much information. You need to generate a simplified report. Then you don't retrieve like, if you're using JPA, you don't retrieve the customer entity directly from the database. You just retrieve the fields that you want to expose to the information. And for that, you're going to create a DTO, like a report DTO. And when I say DTO, I'm not talking about the entity beans DTO, the old kind of things. I'm just saying that we're using DTOs or value objects here because they are simply placeholders for information. They have no behavior, which remind us of an anemic domain model. So in this particular case, the DTOs are just used for reporting and not for executing business logic. So if you have, usually we use DTOs for aggregating things. We want to create a report where we want just the consolidated information of sales per area. And the best way for do that is I just need to sum and group by the things directly on the database. But the result is regarding like the sales information. So the sales transactions are in one table, and you usually just save the information like one sale at a time. But when you extract this information for reading purposes, you create another data model. You create an aggregated data model. That's an example of CQRS. So we're used to creating CQRS models. We just don't know that it has this name. And CQRS becomes particularly interesting when we realize that we don't need to have a single database, a single set of tables for reading and write operations. We can write things to one set of tables, and we can read the things from a different set of tables. And you guess, if you just start thinking about CQRS with separate data stores, it's the very first step for you to be able to later split and then again integrate your microservices database. So basically, when we're talking about microservice database, we're usually talking about CQRS with separate data stores. And when we have a write data store and you have a read data store, which is separate for aggregating purposes, or a kind of cache that we can have for information. And this kind of construction, when we're not talking about microservice database, we usually apply different write and data stores when we're using event source in our system. So it's not a requirement because we can have CQRS without event sourcing, but that's a very popular approach to have CQRS with event sourcing. And to give you a very simple example of what does it mean, the classical example that we have in distributed systems, like the bank account. We can have like, when we model the system as event sourcing, if you think that the amount of money that I have in a bank account, if every bank account starts with a zero amount of money, if I apply all of the transactions in my bank account, sum and subtract the credit and debit transactions, if I apply that successfully, all of them, I'll always have the current amount of money that I have in my bank account. So, but the transactions log can get bigger and bigger. So you won't be, every time you want to know how much money you have in your bank account, you won't start to zero and start applying all of your transactions again, just to calculate that. Because imagine how many users, how many transactions you have in your system. So usually when we have, and event sourcing is the technique that the state of your data is not represented by a column in your database, but instead it is represented by a set of rows in your system. And these sets, when calculated together, they represent the state information. This is event sourcing. Okay? And event sourcing is always usually paired with CQRS because it's slow to be calculated every time. So you just create another table which contains the cached information. Oh, the last amount of money that he had was this one. In every transaction, just update the cache information. Okay? So this is CQRS. You write to here, but you read from the cache. And if you think that, oh, I think this amount of money in my bank account is wrong, you can use an auditing routine for that. You just have to start from zero and apply everything again. Then you can compare the real amount of money with the cached amount of money, just for consistency. And that's basically what every single bank does every night, because he just has a cached information. He just applies the auditing routine and just checks again if the values are correct. And if anything went wrong, they just create a compensating transactions in the log just to check the amount of money that you have in your cache. So this is event sourcing applied to CQRS, and that's a classical distributed system example. So that's what I've just discussed with you, CQRS and event sourcing. And now we know what is strong and eventual consistency. We know what is a CRUD and CQRS. We know that we're creating a CQRS architecture when we're creating splitted, separate microservice databases. And how do I integrate the data for the CQRS model? During this past year and a half, I was able to create from different teams worldwide these 9 different strategies that people are using to create these CQRS architectures in distributed systems. And they are basically shared tables, database views, database materialized views, triggers, transactional codes, ETL, data virtualization, event sourcing, and change data capture. So let's try to very quickly pass over this because I have a demo and I want to have the time to show you that. Shared tables, usually that's the first approach and the fastest one, which leads to a strong consistency because you're applying to the same tables within the same database. You have transaction support on that, but also leads to low cohesion and high coupling because your microservices and your monolith, they are accessing the same tables, because if you change anything here, you have to change here too. It leads to tight coupling, and you don't want don't want to be able to do that. In fact, that's the perfect excuse for you to never change anything anymore, neither here, neither there. So if it's a hack, honestly, it's a hack. But if you do that on purpose, knowing that, oh, I know it's not correct, but I'm gonna first deploy that into production, and then I'll quickly refactor that to a better architecture. So then it's a safe thing to do, but just be aware that if you do that, just blindly is just a hack, and you have to pay it much later, and the cost might be high. Another way for you to create a CQRS, because if I have a customer here, maybe the rest of the system, it needs a part of the customer information to perform correctly. Then you're going to create your the read data model here on your monolith using a database view, which is the easiest one to implement. As of this year, all of the database that I researched, including SQLite and H2, they have view support. So there's no excuse for not using if they have support. You might have some performance issues because depending on your database, view is just an alias for a select query. You have strong consistency because you have transactions. One database must be reachable by the other, and it is also updatable depending on DBMS support. When I say one database must be reachable by the other, if you have a different database here, then you might, to create a view, if you're using Oracle, at least you can create a DB link. And I know that many DBAs will hate me for saying that, but I've done it sometimes, and I've seen people doing that too, and it's possible. And depending on your use case, it works. And again, at least on Oracle, depending on how you create your view is also updatable. You can have writes on both sides, even though most of the times you don't want to do that. Okay, but again, it's possible. Database materialized view has better performance than than just a view. It can have strong or eventual consistency. It depends on how you create the materialized view. If you create the materialized view to be updated on each commit of the source tables, then it's strong consistent. If not, if it's updated on a time trigger or on demand, then it's eventual consistent. Again, one database must be reachable by the other. DB link, and at least on Oracle, it's also updatable depending on how you create the materialized view. You can also have a database trigger. Depends on the DBMS support. Since you can use that inside transactions, is always strong consistent, and one database must be reachable by the other. But again, database trigger is it's very highly not recommended because it leads to, again, to tight coupling. And database trigger is only feasible if you're just integrating one microservice with another endpoint, which usually are monolith, because it quickly becomes unmanageable. If you have more than one microservice to integrate, then if I change here, I have to change here, change there. It just becomes painfully slow and also painfully hard to maintain, because if you change something in each one of the endpoints, you probably have to change the trigger too. And you don't want to be doing this kind of things. Transactional codes also leads to tight coupling. And when I say any code, it means that your code can be a store procedure or a distributed transaction using like two-phase commit protocols. Since you have transactions, you have a strong consistency. You can have possible cohesion and coupling issues just like any kind of code. Just like with triggers and shared tables. You can have possible performance issues depending on how you code. And again, the separate database can be updatable depending on how you implement, because since it's code, you can do anything that you want, and you can have the mess that you want too. Again, it's only feasible if you have just one separate microservice database. If you have more than one, then it quickly becomes unmanageable. You can also have ETL tools like ClickView, Pentaho, and many other kinds of things. You have lots of available tools. Usually requires an external trigger, which is usually time-based or on demand. You can aggregate from multiple data sources. You're not constrained to just a single database or even just a relational database. You can have many different other sources. Since you don't have transactions, it's always eventual consistent, and that's a really all integration because ETL tools are designed to be just one way. This is one of my favorites, data virtualization. Data virtualization means that you're going to create a virtual database on top of your physical database, initially with the exactly same schema. And data virtualization allows you to have real-time access because it's just a virtual layer, but you're reading from your real tables. It's a strong consistent because you have transaction semantics in virtual database too. Can aggregate from multiple data sources depending on the product that you choose. And again, it's updatable depending on the data virtualization platform that you choose. I know that's too small for you to check here, but I just wanted to show you on this picture that you can have many different data sources on the bottom. Then you create a virtual database on the middle tier, and you just access in your application your data using standard JDBC and JPA or Hibernator or whatever you were using, because you can have SQL access to your virtual database. It's really a virtual database. And why I think it's good to have this approach, because you just start that the virtual database is exactly the same copy of your physical database. Then you start playing with CQRS and microservice database. Then you decide, oh, I want to split this part of my system into a separate database. Then you start playing everything else. Oh, but it didn't work well. It's performing badly. Oh, every time I have cascading change. I have tight coupling between the database models. Then if you're using a virtual database, you didn't change anything on the physical database. You just can okay, delete this virtual database and roll back to the previous version, because everything will be working correctly again. So think about a data virtualization platform as a safety net for you to play with splitting your domain model, your database, and etc. And then you can always roll back to the previous version because you didn't change at all the physical database. But if you did it right on the virtual layer, then okay, it's working properly. Then now we can split the physical database. Then it's much safer. It's a much safer approach for you to split your monolithic database using a data virtualization platform. Also, you can have event sourcing, which I just said previously. Event sourcing is always eventual consistent. It's highly scalable because you need a message bus to be propagating the message through your system. And many people advocate event sourcing. Oh, that's the best approach for your microservices and for you to distribute your data. But take care, because event sourcing, it's very hard to do it right, especially if you're not experienced with that, because event sourcing, it can have a tight coupling too, depending on how you model the events. And event sourcing is also unfeasible if you have a current domain model, a legacy domain model. You don't want to be touching that code because it was coded to be using like a CRUD architecture, and you're not prepared to change that to an event sourcing approach. So if you have a legacy code that you don't want to mess up, and if you're just scared of doing event sourcing properly, maybe it's a thing to avoid. I'm just saying the event sourcing is good, but it's not the silver bullet that many people are advocating, because I've seen many people fail miserably when choosing event sourcing for the integration. And the last one, change data capture, which is kind of my second favorite. It's change data capture is a set of tools that just plug in your data source, usually in this case your database, and they connect your database transaction log. So for each one of the insert, update, and delete statement or auto table statement that you create in your database, it creates an event, just like event sourcing. Some people say it's poor man's event sourcing, because you create events for that. It captures and you propagate these events to your message bus. So it's eventual consistent, and since you don't want to lose the message, usually it's tied to a high performance persistent message bus, which these days basically means Kafka. Everybody's using Kafka for this kind of use case. And I'm over time already, but I want to show you this cool demo about Debezium, which is an open source project which implements the CDC pattern. Basically, you just plug it in your database, and Debezium starts to propagate information through your message bus. And if the organizers does allow me to do that, I want to show you this. If it's too small, basically what I have here running, I have a Zookeeper instance running, which is a requirement for Kafka. I have a Kafka message bus running here on my machine, and then I also have a MySQL server running here on my machine. Here I have a MySQL client, a CLI, and I'm gonna show here. Okay. I have some tables. Okay, and here I have Debezium running, which is the CDC tool. Here I have the Kafka, the watcher, which is just a tool that allows me to see which messages are passing through the Kafka bus. And here, just a command line. Okay, what I'm going to show you is if I select from the customers database. Here I have some information available for me, and I want to change the name of n to nmahi, and I have the sequence here. So I've just updated that. Let's see what happened with Kafka. Kafka, I have a new messaging on Kafka running here. So if I'm just gonna show you. Printed here, Debezium creates a message which he extracted from the MySQL database, which just means it always has the preview schema and the current schema, just in case you issued an alter table statements. And also you have the payload saying that before this statement, the value of the row was this, and after that, the value of the row is that. So I can see that I've changed the nmahi name, and you can see you have some internal information, and the operation was an update operation. So you just connect it to the database and just stream the information. And the other question that I received, okay, it sounds cool. And you see, even if the customer row was a big thing, a big row, and if in your CQRS data store in your monolith, you don't need all of this information, because to create the sales report, I just need the name and the email. I don't need the address. I don't need the phone number. I don't need the social security number or anything else. You can just store the things that you want when Debezium propagates the message. And that's the principle of CQRS architectures. You usually have different data models between write and read. So, but another thing is, okay, Debezium looks cool, but what happens if Debezium just shuts down, just stop at Debezium here, and I just keep issuing commands to, like, I'm gonna insert more two things here. Insert Sarah and Kenneth to my database. You can see here that in my Kafka bus I didn't receive any messages, so I just decided to start again my Debezium connector. And when you see, when Debezium gets up back again, I'm gonna hopefully have the message here. So Debezium knows where it stopped, and when it starts again, it just starts in the point that it is just stopped. If I show you it here, just one message. So see, here's the insert statement for before it didn't exist, but now we have like Sarah Thompson, which is was just a create operation. So CDC architecture is my favorite integration technique when you don't want to touch your legacy database, you don't want to touch your legacy code. You can just plug directly into your database and you start streaming the events from your database. Of course, you can configure which tables and which operations you want to Debezium to capture. And currently, Debezium works for MySQL, Postgre, MongoDB. For Oracle, it's beta. And we can also, and SQL Server is the next one. Debezium is a recent project. It's not 1.0 already, but it will be soon enough. And when the Oracle support is considered stable, it will reach the 1.0 version. Okay. And let's get back here. So that's why I really love Debezium. If you ever use it like Oracle Golden Gate, it's kind of the same approach. Golden Gate uses a CDC approach to just extract the information and stream that for you. And that's what I wanted to tell you to show you today. I hope you have all enjoyed. We will be more than happy to have feedback for you on this session. And please join developers.redhat.com for a lot of content on this microservice subject, including the book. And thank you very much.